A Nobel Prize-winning physicist looked at the data from James Webb and reached a disturbing conclusion. The universe is not expanding the way our best model says it should. And the problem did not disappear when Webb looked closer. It became harder to ignore. Imagine measuring the size of reality itself, not a planet, not a star, not a galaxy, the entire universe. Now imagine doing it twice. Once by looking at the oldest light in existence, and once by measuring the galaxies around us. Both methods are precise. Both methods use some of the most powerful instruments humanity has ever built. Both methods have been checked again and again, but they do not give the same answer. One says the universe is expanding at one speed. The other says it is expanding faster. Not slightly, not randomly, not because someone forgot to carry a number. Fast enough that the difference has become one of the biggest problems in modern cosmology. For years, scientists hoped the problem was simple. Maybe the Hubble Space Telescope had made a mistake. Maybe its measurements were blurred. Maybe distant stars were crowded together. Maybe the telescope that gave us the problem had also created the problem. Then James Webb looked. And the disturbing part is not that Webb found a new answer. The disturbing part is that Webb confirmed the old one. The universe is expanding faster than our best model says it should. And if that is true, then something in our understanding of the universe is missing. For a long time, cosmology had a strangely comforting story. The universe began hot and dense. It expanded. Matter clumped into galaxies. Dark matter shaped the invisible skeleton. Dark energy pushed everything apart faster and faster. This model has a name. Lambda CDM. It is not a random guess. It is the standard model of cosmology. And for a while, it worked almost too well. With only a few ingredients, it could explain the cosmic microwave background, the large-scale structure of galaxies, the abundance of light elements, and the way the universe evolved from a smooth, early fireball into the cosmic web we see today. It was not perfect, but it was powerful. Then came one number, the Hubble constant. This number tells us how fast space itself is expanding today. And the strange thing about this number is that there are two major ways to get it. The first way looks backward. It uses the cosmic microwave background, the oldest light we can observe. A fossil glow from when the universe was only about 380,000 years old. From that ancient light, scientists infer what the universe should be doing now. That method gives a value around 67 kilometers per second per megaparsec. The second way looks closer. It measures distances to nearby galaxies. It uses stars that pulse in a predictable way. Then it uses exploding stars, type 1 a supernovae, as cosmic mile markers. This is called the distance ladder, and that method gives a value closer to 73. They sound close, but in precision cosmology, that gap is not small. It is a crack in the wall. To understand why this matters, you have to understand the ladder, because we cannot simply stretch a ruler across space. Astronomers build distance step by step. The first rungs are nearby stars. Then come Cepheid variable stars. Cepheids are special because they pulse. They brighten. They dim. They brighten again. And the rhythm of that pulse reveals their true brightness. If you know how bright something really is, and you know how bright it appears from Earth, you can calculate how far away it must be. It is like seeing a lighthouse in the fog. If you know the power of the lamp, you can estimate the distance from the faintness of the light. Cepheids let astronomers measure distances to nearby galaxies. Then those galaxies calibrate type 1 a supernovae. And type 1a supernovae are so bright they can be seen across vast cosmic distances. That is the ladder. Star to galaxy, galaxy to supernova, supernova to expansion. This ladder helped reveal that the expansion of the universe is accelerating. That discovery helped win Adam Rees and others the Nobel Prize. So when the ladder says the universe is expanding faster than expected, it cannot be ignored. But there was one possible weakness. Cepheids live inside galaxies. Galaxies are crowded. They are full of stars, dust, gas, and background light. From far away, stars can blur together. And if Cepheids looked brighter than they really were because other stars were mixed into the image, the distance ladder could be wrong. That was the escape hatch. Maybe Hubble was fooled. Maybe the universe was fine. Maybe the problem was not reality. Maybe the problem was resolution. Then Webb arrived. James Webb was not built only for this problem. It was built to see the first galaxies, to study exoplanet atmospheres, to look through dust, to observe the universe in infrared light with extraordinary sharpness. But that made it perfect for testing the Hubble tension. Webb could look at Cepheid stars and galaxies that Hubble had already measured. Same targets, sharper vision, less confusion, better separation between stars. This was supposed to answer a simple question. Did Hubble get the distances wrong? If Hubble had been fooled by crowding, Webb should have seen it. Webb should have shown that some Cepheids were not as bright as Hubble thought. The distances would shift, the ladder would move, the Hubble tension might shrink. That would have been the clean ending. But that is not what happened. Webb looked at the Cepheids, and the measurements lined up, not perfectly in every tiny detail, because no measurement is perfect. But they agreed closely enough to make the easiest explanation collapse. The problem did not go away. It got sharper. The new telescope did not erase the tension. It confirmed that Hubble's measurements were not obviously broken. And that is where the story changes. Because before Webb, skeptics could say, maybe the telescope was wrong. After Webb, the question becomes darker. What if the universe is right and the model is wrong? If that question just changed the way you hear the word expansion, hit like. And subscribe for more dark, cinematic breakdowns of the discoveries that are forcing scientists to rethink what we know about the universe. Because from here, this stops being a telescope problem and becomes a universe problem. Think of it like this. The early universe is sending us a prediction. It says, based on what I looked like at the beginning, I should be expanding today at about 67. The nearby universe is sending us a measurement. It says, I am expanding today closer to 73. These are not two random numbers. They are two stories about the same universe, and they should meet. But they do not. The early universe is like a baby photo. The local universe is like measuring the adult in front of you. If the baby photo and the adult do not match, something happened in between. Either the photo is being interpreted wrong, or the adult is being measured wrong, or something changed during the lifetime of the universe that the model does not include. This is why the Hubble tension is not just a measurement disagreement. It is a timeline problem. It asks, did something happen after the cosmic microwave background? Did dark energy behave differently than we think? Did dark matter interact in a way we have not detected? Were there extra particles in the early universe? Is gravity slightly different on cosmic scales? Or is there still a hidden error buried somewhere in the ladder? No one has the final answer. But Webb made the comfortable answer much harder. To a normal person, 67 and 73 sound almost identical. But the Hubble constant is not just a number. It sets the scale for cosmic history. It affects how we estimate distances. It affects the age of the universe. It affects how we understand dark energy. It affects how the early universe becomes the universe we see now. A difference of roughly 8% sounds harmless, but on the scale of the universe, 8% is enormous. It is like building a map of the entire planet and discovering that one continent is in the wrong place. At first, you blame the ruler. Then you blame the camera. Then you blame the map maker. But eventually, if every check keeps pointing to the same mismatch, you have to ask whether the map itself is missing something. That is what cosmologists are facing. The standard model is not collapsing overnight. That would be too simple. It still explains a huge amount of data. That is what makes the tension so disturbing. The model works beautifully in many places. And then, in one of the most important measurements in cosmology, It misses, not randomly, persistently. Adam Rees helped reveal one of the strangest truths in science. The expansion of the universe is accelerating. Before that, many scientists expected gravity to slow everything down over time. But distant supernovae showed something else. The universe was not just expanding, the expansion was speeding up. That discovery forced scientists to take dark energy seriously. And now Rees is at the center of another problem. Because if the local expansion rate is really higher than the model predicts, then the same story that dark energy helped complete may need another revision. This does not mean dark energy is fake. It does not mean the Big Bang is wrong. It does not mean every textbook should be thrown away. The real problem is more subtle. The model may be incomplete. There may be another ingredient, another phase, another interaction, another form of energy, another property of gravity. Something small enough to hide from most measurements, but large enough to pull the expansion history away from the prediction. That is the horror of precision science. The better the instruments get, the less room there is for excuses. Every big scientific crisis begins with a simpler hope. Maybe it is dust. Maybe it is calibration. Maybe it is star crowding. Maybe the sample is biased. Maybe one telescope is wrong. Maybe one method is flawed. That is how science should work. You do not jump to new physics when an old camera might explain the problem. But Webb was the camera built to check the old camera. Its sharper infrared vision should have exposed serious errors in Hubble's Cepheid measurements if they were there. Instead, Webb found agreement. That does not mean every systematic problem is dead. Science is rarely that clean. There are still debates. Other teams use different methods. Some measurements are closer to the early universe value. Some researchers argue the tension may still soften with better data. But the central fact remains. One of the strongest attempts to blame Hubble's resolution did not remove the tension. The crack is still there. And when a crack survives better instruments, it becomes harder to ignore. The most dangerous word in cosmology is unknown. Unknown matter, unknown energy, unknown particles, unknown behavior of gravity. The Hubble tension has inspired many possible ideas. Maybe dark energy was not always constant. Maybe there was an early burst of energy that changed the expansion before the cosmic microwave background formed. Maybe extra relativistic particles existed in the young universe. Maybe dark matter is not as silent as we think. Maybe gravity behaves slightly differently across billions of light years. Maybe several small effects are combining into one large disagreement. Or maybe the correct answer is less dramatic, a hidden systematic error that no one has found yet. That possibility has to remain on the table. But the uncomfortable thing is this: the more we test the ordinary explanations, the more extraordinary the remaining options begin to look. This is not proof of new physics. It is pressure. The universe is pressing on the model, and Webb just added more weight. Now reduce the universe to something human. Imagine standing in a dark room with two clocks. One clock was built from the oldest light in the universe. The other was built from nearby stars and exploding suns. Both clocks are expensive. Both were made by experts. Both have been tested. But one is running faster. At first, you assume one clock is broken, so you build a better clock, James Webb, and the better clock agrees with the second one. Now the room feels different, because the problem is no longer just the clock. The problem might be time. That is why this story matters. It is not just about a number. It is about whether the universe has been telling us the full truth about its history. We are living inside a structure we are still trying to measure from within. We cannot step outside the universe and look at it from the outside. We can only collect light. Old light, faint light, redshifted light, light from exploding stars, light from the beginning of time. And that light is now giving us two answers. James Webb was supposed to be the judge. It could have said, Hubble was wrong. It could have softened the crisis. It could have closed the gap. It could have turned a cosmological mystery into an instrumental mistake. Instead, it did something much more unsettling. It made the mystery cleaner. It showed that the old measurements were not easily dismissed. And in science, a clean mystery is more dangerous than a messy one. A messy mystery can hide behind bad data. A clean mystery stands in the room and refuses to leave. The Hubble tension is that kind of mystery now, not because we know the answer, but because we no longer know where to hide the question. The universe may not be broken, our model may not be dead, but something is not fitting. And that may be even more disturbing, because the best theories in science do not usually fail everywhere at once. They fail at the edges. They fail in the small leftover numbers, in the decimal places, in the anomalies everyone hopes will go away. Then one day, a better instrument looks again, and the anomaly is still there. That is what Webb has done. It did not scream that physics is over. It whispered something worse. The problem is real. And now, cosmologists have to decide what that means. Maybe the answer is hidden in dark energy. Maybe in dark matter. Maybe in the early universe. Maybe in gravity itself. Or maybe the universe has been expanding according to a rule we have not discovered yet. For now, there are two numbers, and between them is a gap wide enough to question the history of everything. If this made the universe feel less certain than it did before, hit like and subscribe. Because the deeper we look, the more reality starts to crack.